Welcome to the Astrophysics Podcast. Each month, I interview a different astrophysicist about their life and their research, and each month I ask the same question of every single guest near the end of the episode. I ask them, in your opinion, why should we care about astrophysics? I always ask that question for a few reasons. First of all, every single person has a different answer to that question. Some people give practical ways that our study of astronomy has benefited society. Other people give a broader picture, saying, these are the big questions humanity wants the answers to, so we should invest in understanding our universe for the sake of broadening our horizons as a species. Still others argue that there's no direct benefit to society, but it's still worth investing time and resources just for the sake of inspiring people to care about science. But everyone has their own answer to this question. And from time to time, this question comes squarely into focus and turns into a public policy question. Why should we be looking up at the stars when we have all of these real concrete problems here on Earth? I bet you Galileo got asked this question all the time. Who cares what all those stars and planets are doing up there? We've got people dying of plague down here on Earth. And Galileo could hardly answer them by saying, look, I'm part of this whole Renaissance thing going on that's going to bring humanity into the modern age. The best he could do is say, I'm interested in understanding how the world works, and I think it's worth investing our time and resources. Okay, so why am I talking about all of this? Maybe you've already figured it out if you pay attention to what's happening in the United States right now. Many people in the federal government have proposed that we slash NASA's funding dramatically. We've seen numbers all over the board, some suggesting we kill up to 2/3 of NASA's budget. Most of our space telescopes that we've spent decades developing would need to be decommissioned and probably driven into a low orbit, burning them up in the Earth's atmosphere. Current missions under development for the past few decades, such as Lisa and Roman, would be scrapped, never seeing the light of day. And we're still not sure why we're being asked to destroy all of these things we worked so hard to build. Now, it's not my job to point fingers or speculate about why someone would want to destroy what NASA has worked so hard to accomplish, but it does bring us back to the original question, which I want you to ask yourself right now. In your opinion, why should we care about astrophysics? You should think about this question. In particular, I want you to think about your answer to this question. Don't answer what you think other people will care about, or what you think is a politically defensible argument, or what argument you would use if you were asked by a funding agency. I want to hear your answer. In your opinion, why do you think we should care about astrophysics? Once you have an answer, I'd like you to take that answer and write it down. It could even just be a sentence or two. Or it could be longer. Once you've written it down, there's a number of things you can do. You can message it to me on Blue Sky if you want, but if you're a U.S. citizen, I think you should send it to your representatives. You don't have to write a brilliant, perfectly worded message to them. It just can be a few sentences, just so long as you're using your own words. Maybe I'm overreacting, and maybe these dramatic budget cuts won't ever actually happen. But they're a lot more likely to happen if no one says anything. So I'll be writing my representatives here in Indiana and making sure they know that the public really cares about NASA and the work they're doing. If you're a U.S. citizen, I hope you write your representatives too. You just have to write them a few sentences. I mean, if your message is too long, they're not going to read the whole thing anyway. Okay, now let's get to the actual podcast. This episode, I'm interviewing Dr. Jared Goldberg, a postdoctoral research fellow at the Center for Computational Astrophysics. Dr. Goldberg builds computer models for stars to calculate precisely how they live and die. In particular, he has a strong interest in our nearby neighbor, Betelgeuse. He has built a number of computer models to try to interpret Betelgeuse's pulsations and variability over the past century. We'll talk with Dr. Goldberg about Betelgeuse and his latest theory that it may have a small companion nearby, sculpting its dusty surroundings. I'm Paul Duffel, and this is the Astrophysics Podcast.
I will try not to say anything horrendously embarrassing or...
No, go for it. You should say embarrassing things. I should...
yeah, what's the audience? What's the vibe?
It's my parents. And
people told... I will say that someone said something to the effect of... or I mentioned you, and they're like, oh, is that the is that the podcast?
I know. I've started.
You have a small cult following. I know.
That's fine. I could take. I love cult followings. Those are the best kinds of followings.
It's true.
All right. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Jared Goldberg, who is a postdoctoral research fellow at the Flatiron Institute. Dr. Goldberg, thank you for joining me.
Thanks for having me.
So let me think, actually, back, because I didn't think about this beforehand. Do you remember when we first met?
Yes.
Okay.
So we first met, it was my first year-ish as a grad student at Santa Barbara. So as a grad student at the UC Santa Barbara, working with Lars Bildston, I had just started, and he had this theory network called the ZTF Theory Network.
Okay.
And we had a theory network meeting that was in the newly constructed Munger Physics residence, which
Right.
is where all of the postdocs and visitors were housed for
Right.
long-term
so this
programs.
is in Santa Barbara. We had this meeting.
In Santa Barbara, we had this meeting.
But anyway, so that's when you first remember meeting me. And
Yes.
so that was at this meeting, this ZTF Theory Network meeting
Yes.
in Santa Barbara. And you were a first-year graduate student.
I was a first-year graduate student. It was a really interesting meeting for me because it also was one that started to humanize scientists a little bit more, because like one of the things I remember was Lars getting so excited to hand Dan Kaysen a guitar and get him on a piano and jam with his friends.
Yes.
So yeah, but
so-
you had been thinking about Raleigh-Taylor instability mixing, among other things.
Okay, and so we ended up talking a little bit about that, and you were Sorry, you were gonna say something?
Oh no,
Okay, fine. That's all right. I'll edit that. I edit the weird, awkward moments.
Good.
out.
That's
I'll
because
have a lot of work to do this episode.
I'm
but that's
sorry, and I'm full of them. It's
That's all right. I am too. Usually, I'm just editing my own. Okay, that whole sentence
Fair
can
enough.
go.
Yep.
But anyway, good. So that was when we first met. So that when you were first year grad student, and so you've been working. So that when you were.
So that would have been 2017 or so.
Okay. And
Maybe 2018.
Okay, and you were a first year grad student working with Lars Bildston, who is
Yes.
a professor at UC Santa Barbara.
Yep.
Okay, so then the first part of this, we're gonna just go back in time and remember how you got to be a scientist. So let me first ask you, where did you grow up?
So I grew up in. I'll say I live in New York now, so I say Los Angeles. When I
Okay.
lived in Los Angeles, I would say the Valley. When I
Okay.
said the Valley, if they were from there, then I would say Winnetka, which is like a small part of the San Fernando Valley. My dad worked in Hollywood at the time. He was
Okay.
in production and writing on sitcoms like Third Rock from the Sun and that 70s show. He was on. He now teaches karate because that's was the next logical step. But I now I work with stars too, and they explode in both cases. So that's my favorite joke.
Okay, great. So you grew up in the your dad worked in Hollywood basically,
Yep.
and but in the LA area.
Yes.
And so do you have a memory of going back of the first time when you thought you're interested in science or astronomy?
Yeah, so my mom told this story at my dissertation defense, but
Okay.
when I always as a kid was really into taking stuff apart and thinking about how things worked, and I also was obsessed with music and stringed instruments and musical instruments in general. I wanted to name my brother El Niño Ukulele Violin Mandolin Goldberg, right? Just after
that was what you wanted his name to be.
Only because it had to be Goldberg, because that's my last name, and everyone, we have to have the same last name. Otherwise, it would have just been the instruments.
Okay.
His name's Shy now. He's
so you were obsessed.
So I was obsessed with stringed instruments and musical instruments in general. And in kindergarten, there was a science fair, and so what I did was I wanted to study how sound waves work in a box.
Okay.
And made little stringed instruments. I stretched rubber bands over different things. I measured how tense they were and how high pitched or low pitched they were. And that was I guess my first foray into science.
So it was the exciting moment where you were science can tell me about this thing that I'm obsessed with and love. It has a scientific description to it.
I mean, in general, I'm just interested in everything. And one of the things I liked, even when I got to college, I didn't know what exactly I wanted to study. And so I started as this major. I was at the Claremont colleges, at Claremont McKenna, and I was a science and management major, which kind of means you can take a lot of classes without red tape. And I you pick a science, and so I picked chemistry.
Okay.
And then I also took a physics class, and I then took another physics class, and it was that one that really made me love physics, because the professor did research in everything. He had worked on solar flares and epidemiology, and he was currently studying like network models of Alzheimer's patients' brains compared to healthy brains. And I was like, you can do anything with physics. This is so cool. I want to understand the universe and the world and how all of it works. This is a way to do it. And I also always liked math, and I always liked sort of systematically understanding things and trying to understand what's going on behind the scenes or the curtain. I would go to a magic show and try and figure out how they did it, or
Right. And I guess physics is the language that can try to penetrate that, like where that describes it, that says like that boils it down and goes, okay, but there's a mathematical description that you can do to understand all of this.
Yeah.
So that is very nice. So then, so now what about your parents? Do you think they were big influences on you?
I would say my parents always were very supportive of education and of me doing the things I wanted to do and exploring in the ways I wanted to. They always fostered whatever I was interested in. They stopped being able to help me with math pretty quickly.
Okay, so neither of them. Yeah, no, my mom was a stay-at-home mom after having done a little bit I was her first kid, so she had done a little bit in the film industry and in a lot of nonprofits. And organizations there, and my dad was working in Hollywood, and then there was this writer's strike in 2001 that leveled the industry, and I remember that being a particularly rough time, and that was around the time he left the field and started teaching karate. But he's been doing that for a very long time and really likes it. So we've always had like a lot of teachers and people thinking in that direction in my family. And so when I was interested in science, they would help me find, after school programs at the public school, which is where I went, and they would be very encouraging of it. And they always emphasized the value of education. So that's a great lesson for, I know a lot of parents, like, so my dad was very math inclined and was like all excited to, help me with homework and things like that.
Yeah.
But, some parents, they're not necessarily mathematically inclined, but then what do they do if their kid decides they're excited? So it's a good lesson that, there are still things you can do if you, seek out programs and things, even if you yourself aren't going to be able to help directly.
Yeah.
So then you got into, mentioned you got into physics. But then how did you make the shift into astrophysics?
Yeah. So there are lots of versions of this story that all depend and it depends a little bit on if I'm on a podcast or in a job talk or something like that, because the real answer is I got to grad school and had no idea what I wanted to do with physics because I was interested in everything.
I was the same way.
I had been tipped off that I should at least talk to Lars, my PhD advisor, and when I was in his group meetings, I became very excited about the types of projects that you could do, the types of problems that, like the types of physics you can do, like think about while doing astrophysics. So I guess this is it. I'm interested in everything, and astrophysics is the way you can think about little bits of everything, right? In order to prevent a star from collapsing under its own gravity, it gets hot and dense enough at the center to ignite nuclear fusion, where you quantum tunnel through the Coulomb barrier between two protons so that the strong nuclear force takes over. Those protons stick together. That provides the pressure support to prevent against gravitational collapse. Otherwise, it would become a black hole. And in that very long sentence, I have hit every single physics that I can possibly think of, and that's very, very cool because you get to put all the pieces together.
Right. So that's how you got into astrophysics, and so then when you started grad school, you were kind of pointed in that direction.
Yeah.
At what point do you feel like you learned how to be a scientist?
So there's a couple directions one can go with that, which is in some sense thinking about cause and effect, thinking about like trying to understand how the world works is something that I've always wanted to do and tried to do and all of that. On the other hand, I'm not even sure now I know how to be a scientist. So it's hard to answer that question.
I guess how would that? What do you think? You at least surely in the time that you've been a
in the
scientist,
field, yeah.
you've learned something about how this is done. So what do you feel like makes up that skill set that a scientist needs?
I think one is the ability to consider alternative possibilities for a theory and then show why one possibility is better or worse by some metric than another, right? What is the evidence we put towards
In other words, in most of our daily life, we have an idea that we think is right.
Yes.
And we go, and even as a scientist, you can fall into that trap where you go like, okay, but this is what I think is, I like this model, or because I came up with this model, I like it better. But then the ability to say to try to step back and be objective about it and say, what is it that I like so much about this model, and what other models could be true, and why do people like those models, or why do people not like those models, and be able to sort of not just have your worldview. You're allowing yourself basically being open mind enough that you can take in those other possibilities and weigh them appropriately.
Yeah, it's really about the ability to take in different possibilities and weigh them appropriately, to build hypotheses and then test them.
Right.
If you see a piece of information I also have a philosophy degree because I took a philosophy class that I loved, and I, again, like how things work, and I get sniped by the structure of arguments. But at its base, a scientific argument is, and all arguments are, a bunch of reasons to believe something, an inference, so going from those reasons to the conclusion.
Okay.
And as a philosopher or a scientist, in both cases, you have to evaluate, are these assumptions good assumptions? Are these reasons to believe the thing, are they true?
Right.
Right. Then, is this inference, is going from the if to the then, is that a reasonable inference? Is that sound? And then the conclusion, either, if that whole process is good, then the conclusion, that's evidence for the conclusion. If the conclusion is false, because that often is that's often the case too.
In other words, when you're looking at the data,
right?
If you've been able to say no, this didn't come out the way I thought it would,
exactly,
or the way the theory predicts that it would,
then there has to be something in the chain of reasoning that was not correct. Right. So either there was a mistake in the inference, or something else you hadn't considered, or one of the premises that you held to be true may not have been correct.
Okay, so you gave a reasonable philosophical definition for what the scientific method and scientific process, how it works.
Yeah.
And so then,
how do you put into practice?
I guess that's the trick, is then putting that into practice.
Right.
And in terms of your everyday scientific work, I think every scientist does it differently, right?
Yeah.
Everybody first they work on different parts of the problem and that sort of thing, but those same principles should, do you feel like they guide your day-to-day choices? I
would say yes, especially towards the beginning and end of a project. It's easy to get lost in the weeds when you're doing the calculation,
right?
Or analyzing the data. I think that there are other skills also that become really important. One is data visualization and trying to make figures that show the thing you're trying to, and that comes into building the evidence for a conclusion you draw, or against it.
I will often tell my students, look at the data. If they ever have a question for me about why is this getting this answer, almost always my first answer is look at your data.
Yeah. No, my answer is plot everything.
Yeah. Make plots of that data. You have all this data you have available to you. Your answers are somewhere in that data. And so it's you look at the data is usually the first step to if you're not sure what's going on. But
Yeah.
anyway, yeah, like that. But that's
I guess the other thing, though, and maybe the harder answer is, I think I've become one of the things I think that makes a really effective scientist is trying to stay aware of a lot of pieces of the puzzle, even if you're working on one. And so that is something that I have tried to foster and learn more and more. And it's hard, but I do think that like I've become a more successful scientist. My ability to do science has grown a lot because I have been trying to keep more and more in mind.
Right,
learn
rather
more.
than just working on this one piece of the problem. Even if you were still working on this one piece of the problem, being aware of all the other pieces that go into it.
Yeah, and maybe it's because I'm interested in everything, and then I can't keep myself
I think it helps.
I do too.
I'm definitely I'm always interested in everything, and so I will generally look for what pieces of the problem I think are well suited to me. But there's going to be lots that are not well suited to my sort of approach. I'm just good to just be aware of how those work.
I agree.
So then, I should ask then. You mentioned it's also important for just the beginning phases. In other words, when you're deciding on a project.
Yeah.
Right. So how do you go about deciding on that? I know that's actually to me actually that's part where you use the scientific method kind of the most, because that's going to affect everything else you do afterwards.
Yeah. Well, sometimes it comes from, it depends on the project that I start. Like my first project in grad school started because I had done a test of a hydrodynamics code that put me on a paper that was a big paper. There was an instrument paper for the stellar evolution code MESA, and in that instrument paper they had also introduced the ability to explode stars, run a shock through them, and then model the light curve of the resulting explosion. And I thought that was very cool, and so I asked my advisor wanted someone to work on that, so it worked out well. I was like, can I do something? And then we together came up with the project. And when I'm designing projects I think I work with a bunch of students now, and I really like thinking about projects with and for students. And so a lot of it will come from what is a big science question I want to answer? What is a really small thing I can do in that direction? And then kind of trying to plot a trajectory from point A to point B.
So the point being that when you're picking something to work on, you have a general trajectory of somewhere that this is going, even if this particular project isn't going to lead you there.
Yeah.
But there's a general path forward that you're moving towards.
Yeah, we're trying to keep the big questions in mind, I guess.
Right. So not just being hyper focused on solving this very particular thing, but having in your mind a motivation for where this scientifically can lead you eventually. Even if you don't have a full path figured out.
Yeah, I think that's fair.
Okay. So now I should say that's sort of how you got to be where you are. You're an astrophysicist.
Yep.
So what do you like?
So they say.
What do you? Some people say that. What do you like the most about your job?
I guess the thing I like the most about my job is that I get to figure out things about how the universe works in an environment where I am surrounded by I try to surround myself with good people and smart, passionate, kind, supportive people. So that's one of the best parts of the job. I also love the blend of research and teaching. So for myself, when I know something, I want to share it, and I want to learn what other people know as well. And so this is a field that lets that happen naturally. It's also a fun way to there was a point when I was a kid when I wanted to be a mythbuster, and this is a way I get to do explosions that don't hurt anyone. So
true.
that's another plus side. But it is a really great. I find that my teaching can enhance my research can enhance my teaching. Just recently, I was trying to work out a how much stuff there would be in front of this companion to Betelgeuse, and it turned out that mathematically that was equivalent to solving a problem that's like when you project an image, like a blob onto a 2D surface, what does that image look like when it's projected? And I was teaching that, and so those were
but the point being
that there's a
seemingly like much more complicated calculation that you were imagining doing, and you can see like actually this is basically what I'm teaching my students right now.
Exactly. Yeah. That's one of the really.
I find that happening a lot more often than I expected too. That you'll be doing some, and of course there'll be other parts of the calculation that you wouldn't ever impose upon your students, but then you'll get to this one part and be like, oh, this is exactly what I'm teaching my students right now. This is really cool. I'm actually using it right now.
Yeah, the student who was going through this projection thing, I like sent her a message on Slack and was like, oh my god, I just encountered this in my own research.
That's cool.
Yeah.
So that's what you like. Is there anything you don't like about your job?
There are things people don't like about every job. One of the things that's very difficult about the field of astronomy and astrophysics in general, and a lot of academia, is that you spend a lot of your sort of formative human years, even after you're just in school, you spend a lot of it in sort of temporary contracts and short-term positions, and it's not like, on the one hand, if you're in industry, you could be fired tomorrow anyway. But on the other hand, that in 3 years, you probably have to leave the state.
Yeah, that's right.
Right. And that's a very hard thing to navigate when you are in a relationship or when you are trying to establish your presence in an area with a group of friends. It can be isolating, sometimes I should say, obviously, there's good reason for that aspect of the job, in the sense that, like, totally.
If you spent all of your time at one institution, you did undergrad, grad school, you did your postdoc, all at one institution, you really don't get a good sense of how
things work elsewhere.
Things work anywhere else.
Yeah, scientifically, I would say it's very valuable to learn, like, every place and group of people have their own things they're really good at, things they think must be true, things they think must not be true, and they often disagree with each other, and the more you go, the more you hear the argument, the reason to believe, the conclusions and the inference, the more you can, like, scientifically, it's very valuable to have this kind of geographic and cultural and intellectual exchange, and that's
and it's true that, like, like the point you made about institutions, like, I find that so true, is that you'll be at one institution and everybody, like, it's just become common sense that X is true, and then you suddenly, the first other institution you go to, like, no, most people don't believe that, and you're like, what? And suddenly you're thrown on your foot, like, we're like, like, wait, I was just at this, like, had this very specific worldview. Just because I hadn't gotten out and listened to what other people were saying.
Yeah, and you see this going to conferences too.
Yes, like, that's right. But generally, it came from the idea that we're moving around a lot.
Yeah. I like traveling, and I like this exchange of ideas, and I moved from Santa Barbara to New York City, and I was long distance with my partner for a while, and now we live together, and it's wonderful, and like, now I'm on the job market again and have to deal with all of the anxieties of that again. And but like, all things considered, it's still,
it's still a wonderful thing to do.
It's still a wonderful thing to do. And also, I'm trying now to shape my career in ways that are more compatible with the lifestyle that I want, because at some point you need to,
well, yes, at some point there is an end. There, you will hopefully end up somewhere, and then you want to know what that looks like.
Right.
Okay. Now we'll shift towards the sciencey part of the podcast, where I ask you about astrophysics. So we're going to start with the following question.
Okay.
When you meet a new grad student or fellow scientist, and they ask you what you work on, what do you tell them?
Stars and supernovae. Stars and exploding stars and their explosions, something along those lines.
Okay, so you study stars and supernovae and try to understand how they work.
Yeah, from a theory and modeling perspective.
Okay.
Although informed by the data.
Okay. All right, but so you're
which is true.
you're a theorist.
Yeah, by training.
And so you try to build theoretical models for stars and how they live and then how they die and explode as supernovae.
And in particular, what it looks like when they do all of these things and how you can connect what that looks like to the internal hidden properties of the stars themselves.
Okay, so like when you say that, you describe internal hidden properties of the stars. What do you mean?
So if you look down, you will probably see a floor beneath your feet. And you probably will not see what's below that floor. Right? And similarly, on the sun, if you look at the sun, all you see is the surface, right? If you look at the moon, all you see is the surface.
Yeah.
But actually, a lot of the processes of stars are driven not by just what's at the surface, but by the entire star itself, right? From the core of the star out through the what's called the envelope of the star all the way out to the surface.
Right. So in other words, if you look do a textbook about stars or something like that, you may get to see like cross section of the star.
Exactly.
But we never get to see that. We never get to chop a bit out of the star and look at what's inside.
Right. So you have to look for signatures at the surface to figure out what's going on inside.
Okay.
Right.
So give me an example of that, or
so here's one example, and I'll liken it to. On Earth, we do seismology. You can look at the waves that travel around the Earth and make inferences about the properties of Earth's core and mantle and crust and all of that.
Okay.
And a lot of that has to do with, like, if you hit the ground with a hammer, you'll see how it rings. And you can connect that to the... you can connect that to the structure of the Earth. Similarly, like if you hit a drum, if the drum is bigger or smaller, it will ring differently.
Or if you pluck a guitar string.
Or if you pluck a guitar string. Yeah, I play guitar.
We covered this in the first part.
Yes. So you can use these waves that tell you something about not just the string, but about the cavity, right? That they're propagating through, that they're moving through. And you can learn about that shape. So you can actually do this in stars as well. If you look at the fluctuations in the light of stars, you'll see certain periodic signals that correspond to actual pulsations, harmonics of the star itself.
Okay, so when we see a star, just to clarify, when we see a star, it's not like, now if we look at it with our eyes, we might just see it looks like it's a certain brightness.
And it will flicker because the Earth's atmosphere is flickering.
Right, the twinkling, that's the atmosphere. And so, but if you look at it with a good telescope, and you look at it, and you keep looking back at it
every
over
day,
and over again, every day.
The star may get brighter and fainter and brighter and fainter.
Okay.
And that can tell you a number, that can tell you how big the star is.
Okay.
Because for something that is doing a breathing pulsation, meaning just getting bigger and smaller, like you blow up a balloon and then suck the air out of a balloon and blow up the balloon and suck the air out of a balloon, that period tells you the radius of the star divided by the speed of sound in the star.
Okay, so now let me just get a sense for what you're describing. So so the star. So you're looking at a star now, but and it sort of it gets brighter and dimmer and brighter and dimmer, and that's oscillations in the star. Like its radius is getting larger and smaller, and
those depend on the internal structure of the star.
And that turns in the internal structure of the star, and roughly you can think of that as like a sound wave bouncing back and forth in the star, compressing, and it's basically one big sound wave, standing sound wave that's compressing and relaxing the star. And so then, so that's telling you something about the sound speed in the star, and it's also telling you about the size of the star.
Yes.
And so. And that, what kind of oscillation period does that give you? Like,
so in the star Betelgeuse, in the shoulder of Orion, you see that signal, and that signal is about 416 days.
Okay, so around once a year
for that star.
For Betelgeuse.
For a much smaller star, it would be a much smaller time scale.
Okay, but let's stick on Betelgeuse because that makes
I work on Betelgeuse,
Okay,
and Betelgeuse will also explode. So, eventually.
So we'll just stick on Betelgeuse because it gives a concrete example. So
Yep.
it over about a year, it'll get brighter and then dimmer,
Yep.
and then the next year it'll get roughly get brighter and
Yep.
dimmer again, and then it'll oscillate like that.
Yep.
And every month you can go back and look at it and just see how bright it is, and then you can
Yep.
use that and you can kind of fit that to a sort of almost sinusoidal
Yep.
variation in the star's brightness.
Or you can just take the data, and then you can take a Fourier transform of the data,
We're
meaning
not
that
going to talk about what a Fourier transform is.
You can find what all of the periods are. So if you have a time series, you find what all of the periods are in that time series.
So in other words, if you look at it wiggling, it'll wiggle up and down like once a year maybe, but then there'll be longer period variations. So it'll wiggle up and down, but then it gets over a very longer time scale. It's getting brighter and brighter, and then
dimmer and dimmer.
But it's oscillating back. It's oscillating up and down around that sort of envelope.
Yeah. So the long period that's longer than a year, that has to be anything that's longer than the fundamental mode, which is sort of the slowest pulsation you can have, tends to have to be something happening outside the surface of the star.
In other words, if it were something interior to the star, it's hard to make something that slow because
if you pluck a guitar string, there is a lowest note you can hear, and that lowest note you can hear is the open string.
Right. The only other modes you can make is if you hold down part of the string, and then it'll pluck at a higher frequency.
Exactly.
And so this fundamental mode you're talking about, that's if you don't do anything and you're just watching the whole string oscillate. And
exactly.
So that's the same analogy with Betelgeuse. You're just watching the whole
star oscillate on a 416-day period.
So that's the lowest period you could imagine getting by a conventional just oscillation in the star.
Exactly. So then there are two signals you see in Betelgeuse that are actually longer period than that.
Okay.
One of them is a 36-year period that's inferred to be rotation of the star itself. So
just to clarify, a 36-year period.
Yes. We've been looking at Betelgeuse as long as humans have had eyes.
Sure. Okay, but it's a very long period to have decent data on. So
yes.
So if you go back a century, then we would see three oscillations of it, roughly.
Correct. Yep.
And so
or three rotations.
Yeah.
This is rotation.
This is not an oscillation of it. So we were gonna talk about this. But, but anyway, but that point is it's a very long period, but you're saying it's not caused by oscillations of the star.
No. So the 36-year period is caused by rotation of the star, probably.
Okay. Probably.
There's other evidence that the star is rotating.
Yeah.
Such as the fact that Betelgeuse is actually really, really, really big, which means that with certain types of telescopes, you can actually resolve the surface of the star.
Right.
And you can actually measure.
Basically take a photograph of the star and actually see a resolved image of it. It's still fuzzy.
More or less. It's still fuzzy. Yeah. It's like the resolved image of the black hole. You see the fuzzy donut.
Right.
Except this is just a fuzzy blob.
Right.
But you can also measure, with those same tools, you can measure velocities from different lines in Betelgeuse's spectrum, and you see that one side of Betelgeuse is rotating away from you, and one side is rotating towards you.
Okay, so then you can measure how fast it's spinning.
So you can measure the spin.
So actually, you should be able to get a decent measure on its rotation period from that.
Yes, and that measurement also gives you something like 36 years.
Okay,
so those are consistent with each other.
Okay, so we know that 36-year period has something to do with the rotation of Betelgeuse.
Probably. There are some people who... So the other thing is that these stars are really like boiling, bubbling with huge plumes.
Right.
And it could also be that those huge plumes look like part of the plumes moving towards you and part of the plumes moving away from you. So this is a source of controversy.
Coming up with some theory that says that that's actually not how fast it's rotating.
Exactly.
But you're just seeing a bit of it coming out at you.
Correct, and a bit moving in.
I see.
And I think that's one you can resolve with more observations.
Right. If you keep looking back at it.
If you keep looking back and the dipole is consistent, if it's always right side moving towards you, left side moving away, probably that's stable.
Right.
If it's a convective churning plume. At some point, there's something moving towards you that'll eventually be moving away from you.
Right,
so you should see something different.
Okay, so it makes a prediction, but okay, let's imagine
that one. So it's rotating.
But hang on, so that period has something. We imagine it like the scenarios that has something to do with rotating. Does that mean that there's something on the surface that's coming into view, or?
That's a little bit harder. Maybe it could have to do a little bit with Betelgeuse being a little bit oblate because it's rotating, and so you see a bulgy side and a less bulgy side, and you sort of see, there is.
So, but anyway, there's some aspect to its shape or some structure and
following its rotation period,
and that there's something about that has something to do with that comes into view once every 36 years.
More or less,
like that.
Or your view changes and refreshes every 36 years or so.
Okay.
There's a second period that's something I've just been obsessed with lately. That's more, in my mind, more interesting than the rotation period, which is a 2000 or 2100-ish day period. So about 6 years.
About 6 years. So once every
5.5 to 6 years.
Okay.
So once every 5.5 to 6 years. It's not so much a once every 5.5 to 6 years, but it's just that the behavior goes in and ebbs and flows
up and down about once
on this every 5 to 6 years.
So now we're thinking of 3 different periods.
So 3 different periods. There's a pulsation, which we understand, we think, more or less.
Yeah.
More or less. There's rotation, which is the long one, and then in between there's this what's called a long secondary period, or LSP.
Okay, and we just call it that because we don't know what it is.
Exactly. It's longer relative to the fundamental mode, and it's secondary, so it's not quite as not quite as high amplitude as the fundamental mode.
Okay.
And this long secondary period happens in about 30% of red giants, red supergiants, AGB stars, big, cool, evolved stars. So it's a ubiquitous.
We're not just thinking about this in terms of Betelgeuse. It happens. We look at other big puffed up stars,
and they have it too.
We see this fundamental mode, and then we see this long secondary period.
Yep. At least in stars that show a fundamental mode, in about 30% of them, you can also see a long secondary period.
Okay.
Now, that's interesting because it means it's a pretty common phenomenon, but it's also happening they're persistent. Like for smaller radii, all of the timescales are shorter, just because the star is smaller, so you can cross it faster.
Right.
And so the long secondary periods in smaller stars are only a year even for some of them, or a few years. And so then you can, if you look for 30 years, you actually get 10 of those and you can see a lot. So we don't need the hundreds of years of observations of Betelgeuse, which has a 6-year period, to see a bunch of cycles.
You can go to smaller stars, just like, we can do this again with this guitar string. You can go to a shorter guitar string with the same tension should give you a higher frequency. In other words, a shorter period to oscillate. And so you can look at those, and you don't have to look at them for as long to see these longer... these longer trends,
Okay. And there has been a lot of work done connecting this long secondary period to cycles in the dust activity of the stars.
Okay.
So the stars are somehow making some dust around them, and there seems to be some cycles in the dust forming and disappearing, swinging into view and just occulting the star, swinging out of view and revealing more starlight.
Okay.
And there's also been some connections between, and the hypothesis, the leading hypothesis in the field was that this is caused by a companion in orbit around the star.
Okay, so hang on. That would imply
that
30%
of stars have, and this companion doesn't have to be very big. It could be a comet-like companion or a planet-like companion, or a much smaller star or something.
Okay, but it does have to be.
But it has to be something.
It has to be like.
It has to be sufficiently big to interact.
And it has to be reasonably
close.
I was going to say
or far
along the line of sight, right? It would have to have to move in front of the star.
Right. Well, so there's a question does it actually have to be a transit? Does the planet have to actually get in the way of the star? Or does the smaller star have to get in the way of the brighter star in order to cause things? I'm not sure that that's necessarily true.
Okay.
Because you can have something that's like, if it's...
As long as it's producing dust or something
as long
like
as
that.
producing dust and then can shape that dust in a pattern related to it, it can go downstream a little bit.
Okay, so then, in other words, it doesn't have to be...
It doesn't have to be spot on.
The planet itself doesn't have to be right in front of pass right in front of the star.
Exactly.
The material around it has to affect stuff along the line of sight between us and the star.
Exactly.
And so that means it doesn't have to be perfectly aligned.
Yep.
But maybe in 30% of stars there's something
enough alignment.
There's something that comes in close.
Yeah.
But they're all in these long periods. So why? It seems weird that they would that requires them to be at a certain radius from them, right?
Yes, and it turns out that so for red giants, AGB stars, and red supergiants, their temperatures are actually pretty similar.
Okay.
Which means that the distance from their surface outward, temperature falls off with distance, but you're starting at more or less the same surface temperature. So there is actually kind of a characteristic distance away from the star where dust will start to form.
Okay, so all of these different stars tend to form a bunch of dust at around
a similar radius. And so if you put the companion near that radius, then that will be the best place to cause this effect to happen. So then there also, for a while, was the leading hypothesis was actually that it was like a comet-like companion with a dusty tail. So you swing into view, and then you block the star and go on. But the other thing that we can do, so that makes a prediction, and then to test that, you can look at the radial velocity. You can measure actually how fast stars are moving towards or away from you on your line of sight. Right. You measure the radial velocity of the star, along your line of sight, and you see that the stars are swinging towards and away from you a little bit, or at least there is a
just
period.
To clarify, when you're saying watching the velocity of the star moving towards you and away from you, this is like a technique that that people have used to search for planets, for example, orbiting those stars.
Exactly.
Is the wobble or the back and forth motion given to the star by the fact that it has a massive enough companion to when it's going around, when the companion's moving away from you, the star is moving towards you.
Exactly. Right. Stars, so binary stars and even planets around stars all orbit a common center of mass. Right. And that common center of mass does not have to be smack in the middle of the star. Right. So like the Earth and the Sun orbit a common center of mass. That center of mass is much closer to the center of the Sun than it is to the Earth.
It's a little bit offset from the center of the Sun.
And that's mostly Jupiter's fault.
And that's right. But then the point is that, say Jupiter and the Sun orbit one another, the Sun just has a little bit of motion around every time the Jupiter orbits once, the Sun also kind of wobbles around its center of mass.
Exactly.
Just a little bit. So then the point being that you can do this measurement to detect whether there's something massive orbiting a star.
And the other thing is you not only you can measure that period, you can also look at the phase relative to the brightening and the dimming. Brightening and the dimming, right? So you can ask, is it bright when the companion star is in front of Betelgeuse? Is it faint when the companion star is in front of Betelgeuse? Right. If it's an eclipse, that means it should be faint when the companion's in front of the star. Right. And so we actually looked into that, my collaborators and I, and what we found was that in most cases, it's actually brighter when the companion it's in the brighter phase when the companion is in view. It's in the dimmer phase when the companion's behind the star. Right. So there was this great dimming of Betelgeuse that happened in 2020, and the companion would have been right behind Betelgeuse when it happened.
Right. So this is starting to throw a wrench into this idea, right? At first, you say the whole idea was that this thing's blocking stuff, so it shouldn't be behind Betelgeuse when it's its dimmest.
Right. But the assumption there that was wrong was that the companion should be the thing dragging and producing the dust.
Okay.
When you get rid of that assumption,
Yes.
invalidated by this new data, then you say, oh, but the star itself is convective, it is pulsating, it is doing all sorts of stuff at its surface, and all of that stuff can put out material into its atmosphere faster than the orbit of the planet or of the companion.
Right.
So now you have the star producing material that becomes dust.
Okay.
And so the idea is actually that where Betelbuddy is, where Betelgeuse's companion is for Betelgeuse, you won't get a great dimming, because if the star tries to put off some stuff there, well, there's a companion in the way. So it's a fundamentally different picture than this comet-like.
Just to clarify everything you're saying there.
Yeah.
So this so again, going back to this, there was this oscillation at this fundamental mode,
right,
which is
this
about
400 days.
Once every year.
Yeah.
Each time it's oscillating,
it can put out some stuff.
It might be churning out and throwing out dust every year, and reinvigorating that area with a bunch of dust.
Yep.
And so that whole, and not just one part of that, but all of the region all around the star, everywhere, it's getting full of dust.
Potentially. Right. Depends on how blobby the star is. Depends on.
And so that could be going on. So then the whole star may be surrounded by a cloud of dust. But then when
the companion is just sculpting that.
So the idea then is not that the companion itself is putting out this dust
or carrying it,
but that when the companion comes into view, it's not blocking the light from the star, but it's actually sort of
making it easier.
Somehow removing this dust around in the vicinity of it, so that you then have sort of a hole that you're looking through almost.
Right.
And the star will look brighter because this companion is somehow. And
this is the part that I think we still need to do a lot of work on, is figuring out just how this interaction happens.
Right.
And it may depend on the nature of the companion.
Right.
So if the companion is really hot, for example, it might be heating up the dust, and then it's just turning dust into gas.
Okay, so it's just like disintegrating.
It's not doing anything, but it's just disintegrating it, and it's easier to see through disintegrated dust than it is to see through dust.
I see.
On the other hand, it could be that the gravity of the companion is interacting with all of this material and causing it to condense or move out of the way or fall onto the companion star or any number of other processes.
So it might be carving out some region in the vicinity of it due to its gravity.
Or sending a wave through the dust based off its orbit because of its gravity.
Okay.
And so these are things I think that it'll be really exciting to see to see more work in this space on, is figuring out, like, how does it really cause the brightening and dimming? Because from the data, what we can say right now is it's brightening and dimming. It tends to be brighter when the companion's in front. It tends to be dimmer when the companion's behind.
Right. And so hang on. Is this all of this specific to Betelgeuse? I mean, can we look at it with other stars?
If you look at other stars, you also see this same phase correlation. You see that there is a spread.
In other words, if you try to for a lot of these, maybe not every star,
not all, but for most,
for a lot of them, if you try to model it as there's another body orbiting around that star,
correct,
what you find is that that body is behind the star
when it's dim.
When it's dim,
the companion's behind the star when it's dim.
So which is just it's interesting, because like at first that seems like that's so bananas, and then so you think, okay, so then if you still want it to be caused by this companion, and the fact that it
can't be an eclipse, it's the opposite.
It can't be an eclipse. It has to be something the opposite. And so right now we're trying to figure out how you could model that and sort of understand, like, what could this thing be doing to cause there to be less material in front of us.
Yeah. Or another version of it is actually when you. Another way you can use the star's gravity to shape this is, like, you could imagine a scenario, and you'd have to work out if this is actually plausible in reality. You can imagine a scenario where you actually have a dust cloud that's orbiting out of phase with the companion.
Okay.
And so it's sort of just like the dust cloud is sitting at some stable point with respect to the companion's orbit, and so then it swings. The dust cloud swings into the view when the companion's behind the star swings out of you when the companion's in the
My
way.
listeners are not going to be able to see that hand motion.
Oh, sure. I was making hand motions.
But that's fine. But the point being that the idea is that the companion is on one side of the star, and then exactly opposite the star, there's some kind of accumulation of dust.
Yes.
And it may be at a sort of point where maybe that dust can accumulate just on the opposite side of where the companion is.
Yeah.
And if that's the case, then that
would be another
that'd be
way.
another potential way you could try to do that.
I personally don't think that one works for Betelgeuse. So there is actually a dynamically stable point around there are multiple points around two orbiting bodies called Lagrange points that are effectively 0 points in the potential. Effectively, they are your
point is that they're stable.
The point is that
stable places where things can orbit stably and not drift off and fall into other places.
Exactly.
And so one point that is stable is this what you call a Lagrange point, but that's opposite.
What's called the outer Lagrange point. So if you have star A, then star B, then this outer Lagrange point.
Okay.
So star B is now the big one, and star A is a little one, I guess, in this scenario.
On the other side opposite the smaller body, there is this point, this outer Lagrange point, and that's one point where you could imagine just trying to accumulate there.
Yeah. However, you can do physics and see whether or not that point is stable or unstable. Where if you put an object there and then perturb it slightly, will it run away onto one of the things, or will it stick? Will it stick around that point? Mm-hmm. And I think for the mass ratio of Betelgeuse and its companion, stuff would run away. So I don't think you actually get a stable orbit there. But for some other systems, you might.
You could imagine if it's continuously being injected with new material, it may not matter if it's stable. It might just be a place that material tends to flow through, and so it could be a place where stuff tends to accumulate.
Yes. Yes, and I think that if that turns out to be the answer, to me that's the coolest answer, because it's like a piece of physics that you learn in a classical physics class. Pure physics, orbital mechanics, that turns out to be so astrophysically relevant and interesting.
Yeah.
So I would love that to be the solution.
So often it can, like those sorts of things do end up being the solution. Maybe not every time, but they do often. It comes up a lot, which is why astrophysics is a thing, right?
Oh yeah. Well, this is what I say. Like, it's a really fun test bed for all sorts of physics problems, right? You get to think about all of the physics, and vice versa. You get to learn about physics by studying these things in space.
Okay, so then let me finish up by asking this question.
I didn't even get to the explosions part.
That's okay.
That's probably for the best.
We can have you come back sometime. Let me ask this question. In your opinion, why should we study astrophysics?
I guess we can split that in a couple different directions. One is, why should you, someone I'm telling to study astrophysics, study it, and why should we as humans, as an enterprise, why should there be people doing astrophysics? And to the first question, I would say, there's a lot that's fun about it, and you can learn a lot about the universe, and if you love it, you should follow the love. For why we as a society should study astrophysics, I mean, this comes up a lot because there are so many problems here on Earth that maybe we should be spending our effort solving. There's also a lot of people on Earth, and there's a lot of skills you build doing astrophysics that help you think critically in your daily life, that help you think critically about solving problems in the real world. And some of it is also like when you get a bunch of people together who are really passionate about a hard problem, and astrophysics has a lot of hard problems, they think of really creative and clever solutions to those problems that end up having implications for all sorts of things you may never expect. And then also there's the night sky belongs to everyone and should belong to everyone and has always belonged to every civilization throughout history. I think it's one of the most fundamental, unifying things we as people can do sometimes is like look up and we see the same stars and they're behaving the same way. And I think that like learning about the universe helps us, you know, it helps put certain things in perspective, and it also helps like...
It's interesting because you started from a common sort of talking point you hear a lot, which is like, what? We have problems, so many problems here on Earth. Let's solve those problems first before we try to go to the moon or whatever. And you hear that so often, which first of all, you'll never solve all the problems. So but secondly, but it's interesting because that framing of it makes it sound like these problems are really big that we have to deal with. And why are we studying this little stupid thing of astrophysics? But then when you talk about it in terms of this is something that belongs to everybody and has belonged to every civilization on this planet, and is this big thing that connects all of us, that makes all of those other little problems seem much smaller.
I mean, and they are, and it's not to minimize them in a real sense. Like the material problems are, need material solutions.
Yes.
But how about this?
Okay.
So there's a saying in Judaism, I'm raised Jewish, that goes something like, it's not incumbent upon you to finish the task, parentheses, like of repairing the world, right? Nor are you free to abstain from trying. And I think there are a lot of people in the world doing a lot of pieces of the puzzle of repairing the world, and it's a global effort. And one of the things I see astronomy, astrophysics, science doing pretty effectively is being able to spread awareness of cause and effect, of how to think about the universe in a way that grounds you in things that are true, to evaluate those biases critically, to look at information and then process it, figure out what are the reasons to believe a conclusion, what are the reasons, how does, what is that structure, and then are those good reasons? Is the inference sound?
Right.
And evaluate that. And I think that one of the things that science and astronomy and astrophysics especially do pretty well is modeling that process, teaching that process, spreading that ability, and doing it in a way that connects everyone in a way that we all can...
That's a good point, because I think it's interesting the way you point that out, because everybody thinks that they think critically and that other people don't. But it's nice. The thing is, it's very, very easy to get biased when the things you're talking about are things that affect you and the people around you directly, and that are that impact on your day-to-day life. But
it's also
but then when you're talking about big, broad things that are a little bit more of a neutral ground, we can all look at the sun and know it's all our sun, and it's not like that, and we all can just be genuinely curious about how it works, and you certainly, scientists still have biases, of course. But it doesn't have the same kind of bias that you get when you deal with day-to-day terrestrial problems.
Yeah,
and so
the process of doing it hopefully forces you to reevaluate your own biases in your work, in your life, and in general. And I know we all are subject to tremendous amounts of bias, and we try to correct for that as best we can. And it's nice to have the shared common ground of hey, what's going on with that star?
All right, great. I think that about wraps it up. So thank you so much to Dr. Goldberg for joining us. I had a lot of fun talking science with you, and I hope you'll join me again sometime.
Yeah, thanks for having me, and I had fun, and likewise hope to join you again.
So glad we got to talk about Betelgeuse, and I was very excited to hear about its potential Betelbuddy. So thank you so much to Dr. Goldberg, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. If you want to connect more or have astronomy or astrophysics questions, follow me on Blue Sky at paulduffel.bsky.social. Music on the Astrophysics Podcast was written and recorded by Britton Ashford from her album Trotter. All songs are used with permission from the artist and producer. If you enjoyed it, check out Britton Ashford's latest music. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, professor of physics and astronomy at Purdue University.